So Ashoke is the recipient of the Frontier of Science Award, and he will tell us about the award later. And that's for you.
Thank you very much. Okay, so it's a great honor for me to be here giving this talk. So today I'm going to talk about string field theory, but I'll try to focus on a particular problem that came up in Victor's talk earlier in the day, okay? And that is how string field theory can be used to fix ambiguities in the worldsheet waterproof theory. So let me begin by describing the motivation for string field theory. So I think it's familiar that in the conventional approach, if we try to compute a string amplitude with a given set of external states, then we have only one term at every loop order. And this is given by an integral over the moduli space of a Riemann surface with punctures, where the vertex operators are inserted. And this has the advantage that it avoids having to sum over large number of Feynman diagrams. At any loop order, we have only one diagram. However, often these integrals over the moduli space of Riemann surfaces run into divergences from the boundary of the moduli space. And here, when I talk about the moduli spaces of Riemann surfaces, I also include, for example, the locations of the vertex operators, because the general notion of moduli space of Riemann surface with punctures also requires also includes the location of the vertex operators. So these divergences, for example, also include those which come when the two vertex operators collide. Okay, so all of them will be treated on the same way. Now, in some cases, these divergences can be tackled by analytic continuation in the external momenta. But when this fails, we need to take help of string field. Okay, and this is what I'll try to describe. So let me say a few words about what string field theory is. So you can think of string field theory as a regular quantum field theory with infinite number of fields, and it has phi to the n type of interactions for all n. So that looks like a complicated kind of field theory. You have many Feynman diagrams, and indeed the perturbative amplitudes in string field theory are given by sum of Feynman diagrams. But what distinguishes string field theory from a regular quantum field theory is that the sum of Feynman diagrams can be reorganized into integration over the moduli spaces of Riemann surfaces. And in fact, each diagram covers part of the integration region. So the integrand always is the same for every Feynman diagram, but each diagram covers part of the integration region. And when you sum over all the Feynman diagrams at a given loop order, you cover the full integration region. Okay, in fact, this is the way string field theory is formulated in the first place. Okay. So in this sense, string field theory, once you do the computation and sum over Feynman diagrams, it is designed to reproduce exactly the worldsheet results. Okay. So you are not really changing the theory. String field theory is the same, is equivalent to the standard worldsheet formulation. And as in worldsheet string field theory also has no ultraviolet divergences. And this can be seen very explicitly in the context of string field theory, because the interaction terms in string field theory are exponentially suppressed at large Euclidean momenta. So you never get divergences from integration over large Euclidean momenta, okay, which is the source of ultraviolet divergences in regular quantum field theory. Now, we have already said that the string field vortices are phi to the n type for all n. Okay, but let's say something about the propagator now. So the string field propagator, it has the form of the inverse of L0. L0 is the zero mode of the Vira-Zero operator, the Vira-Zero zero mode generator. So for open strings, the propagator is L0 inverse. For closed strings, the propagator is L0 plus L0 bar inverse. Now these may look a little bit unfamiliar, but this reduces to the familiar form once you note that the L0 eigenvalue on a given open string state is in fact k square plus m square, where k is the momentum that the state carries and m is the mass of that the state has. and the physical state conditions which put L0 equal to 0 or L0 plus L0 bar equal to 0 just corresponds to K square plus M square equal to 0. That's the on-shell. So indeed at the level of each component, the propagators that we have seen drawn here or given here are the standard propagators in a quantum field theory. Now, I said that the string field theory is designed so that the Feynman diagrams reproduces the standard worldsheet answer. But one can be more specific here and see where the worldsheet description emerges. And to see how the worldsheet description emerges from string field theory, we need to use the Swinger parameter representation of the propagator. In particular, if we take the open string propagator, L0 inverse, we have to express this as an integral over this parameter t, dt to the minus t n naught. This is the standard Swinger parameterization. But I'll also use this variable q, which is related to p by as q equal to the minus t. So you can rewrite L0 inverse as integral 0 to 1 dq q to the L0 minus 1. And it's the integration over the q variables that become integrals over the moduli spaces of Riemann surfaces after we make a suitable change of variables. So this is the way string field theory makes connection to the worldsheet theory. The Swinger parameters of the string field theory become the usual moduli parameters of the Riemann surfaces in the worldsheet description. So let's review this again. So from the string field theory perspective, it's natural to think of the propagator as L0 inverse. Whereas what we are saying is that from the worldsheet perspective, it's more natural to think of the propagator as integral dq q to the L0 minus 1, because these q's are the moduli of the Riemann surfaces. Now, if you examine this identity, we can see that as long as L0 is positive, this is an identity. Okay, it's clearly true. You can do this integral for positive L0 and you can see that this is L0 inverse. However, when L0 is negative, we can see that the right hand side actually diverges from the q equal to 0 end, because this becomes dq q to a power of q that is less than minus 1. So this integral is clearly divergent from the q equal to 0 end, but the left hand side is perfectly finite. So in this case, we can use string field theory to get finite results, and this in fact is equivalent to analytic continuation in K when that is possible. So we see already that at this level, the string field theory does better than the worldsheet theory. The worldsheet theory gives a divergent result, whereas string field theory is finite. Now, the more interesting case is that of L0 equal to 0. When you consider L0 equal to 0 states, then we see that the both sides diverge. This side is infinite, this side is also infinite, because this is logarithmically divergent integral. So neither side apparently wins. Nevertheless, in string field theory, the divergence comes from an internal on-shell propagator, right? Because L0 inverse is the propagator. So when L0 is 0, that means that the propagator is going on-shell. Now in quantum field theory, you know that whenever you have an on-shell internal propagator, that means that you are doing something wrong. And usually quantum field theory also tells us what we are doing wrong and how to fix it. So whereas at the level of this equation, both sides look divergent, we expect that from string field theory, we will have a proper understanding of what the origin of the divergence is, and hence we will be able to fix this. And this is in fact the insight that we are going to use to resolve all the divergences that arise in the worldsheet theory. And I should also add that all divergences that we ever encountered in the worldsheet description of string theory are of this type. So all of those divergences can in principle be resolved once you go to the language of string field. Okay. So now let me say a few words about d instantons. Okay. Here in fact Victor has already introduced the basic ingredient, so I just have to repeat what he said. So d instantons are like regular d branes, but it has Dirichlet boundary condition along all non-compact directions, including Euclidean time, which means it's localized in space and time, at least for the non-compact part of space and time. And as a result, it has finite action okay, which takes the form of some constant over the G string, where G string is a string coupling. So you can think of the d instantons as finite action classical solutions in string theory. So these are analogous to instantons in quantum field theory, and they give non-perturbative correction to string amplitudes, okay, just like ordinary instantons do in quantum field theory. So typically the d instanton contribution to amplitudes have the form of an exponential suppression factor e to the minus c over gs times a power series in the string coupling. And because the dynamics of d branes is described by open strings that live on the d brane, okay, d instantons are no exception. The fluctuations around d instanton background are described by open strings living on d instantons. So the worldsheet theory of closed and open strings provide the formal expressions for the d instanton contribution to the amplitudes. In other words, if we want to systematically compute the power series in G string, all that you have to do is to carry out integrals over the moduli spaces of Riemann surfaces with boundaries, and these boundaries will end on the d instanton. So you have to put Dirichlet boundary condition on all the non-compact directions at these boundaries, and this will generate the series expansion in Gs that multiplies this e to the minus c over Gs factor. So this part, in fact, Victor also emphasized in his talk. So now let me describe the systematics of the instanton amplitudes, again something that Victor had reviewed, okay, but I'll repeat this. So one difference between the d instanton induced amplitudes and the amplitudes in the presence of d branes or just closed string amplitudes is that because we put Dirichlet boundary condition on the non-compact space-time directions, individual worldsheets break both space and time translation. So you don't have energy momentum conservation on the individual worldsheet amplitudes. So this is what I have said, and as a result, disconnected worldsheets also contribute even for generic values of external energy and momentum. Normally in quantum field theory, we don't include disconnected Feynman diagrams, and in the same spirit, we don't include disconnected worldsheets in string amplitudes. And the reason is that each connected part has its own energy momentum conservation. So for generic values of external momenta, okay, satisfying an overall energy momentum conservation, the disconnected worldsheets simply give you zero answer. That is not the case here anymore, and hence the disconnected worldsheets are on the same footing as the connected worldsheets. Another way of saying this is that because we put Dirichlet boundary condition at the end of the disk, okay, like suppose you have two disks, product of two disks like this, on this ends on the d instanton, this ends on the d instanton, and they are at the same space-time location. So even though they are disconnected worldsheets, in the target space they get connected because they end on exactly the same space-time points. So this is the reason you have to include disconnected worldsheets in computing the d instanton amplitudes. And this gives the following rules for finding the leading contribution of the d instanton amplitudes, because if we are allowed to use disconnected worldsheet, then we know that in string amplitudes, the one with maximum Euler number contributes the most because they have the lowest power of string coupling, okay, because the power of string coupling is g to the minus the Euler number. So we can maximize the number of disks because each disk has Euler number 1. So each disk will give a factor of 1 over g string. So for any given amplitude, we can maximize the number of disks to get the leading answer. Furthermore, annulus has Euler number 0, so they go as gs to the 0. So you can use as many annuli as you want without costing any power of string coupling. So the leading contribution to a d instanton induced amplitude has this structure. You have this e to the minus c over gs. Okay, this you can think of as exponential from the disk. Then you have the exponential of the annulus because this is of order 1, and then you have the product of this quantum function. So these crosses are the closed string vortex operators. Okay. So this is the structure of the leading term in the d instanton expansion. At the next order, okay, we have more possibilities. So here, for example, what I have done is that I have taken a two disk one-point functions and replace this by a disk two-point function. Okay. So essentially, we lose one disk, right? Because you have converted two disks into a single disk, okay? Because two vertex operators are put on the same disk. So you lose the power of G string here compared to the leading answer. Here we have replaced a disk by an annulus. Okay, so this means that 1 over GS we have given up and we have gotten a GS to the 0 contribution. So that's again suppressed by power of GS. And then here we have the product of the disks as usual, but then we have taken a disk with two holes. Okay, this has chi equal to -1. So this again gives a factor of GS. And there is one more diagram, okay, where you connect these two holes by a handle. Okay, that's a torus with a boundary. That's also of the same order. So this way we can write down the expression for the d-instant on induced amplitude to any order in the string coupling. And finally, I should just say that the energy momentum conservation, as I said, individual diagram worldsheets do not conserve energy and momentum, but eventually energy momentum conservation is restored after we integrate over the d-instant on position. Okay, because that's what produces the final delta function. Now, let me turn to the spatial difficulty that arises for d-instant on induced amplitudes. So, because we have Dirichlet boundary condition on the non-compact directions, if we take open strings on the d-instanton, they do not carry any continuous momentum because their ends are pinned to a given point in space-time. Okay, so they don't move along the non-compact directions of space-time. And that means that when you write down the expression for the L0, it does not have a k square term, okay, with a continuous variable k, and hence we cannot analytically continue in k to make L0 positive. So if some open strings have L0 equal to 0 or L0 negative, then we basically have to deal with it directly. Okay, so if you have an integral of this form, okay, that comes from the worldsheet, then we cannot simply say that we will try to analytically continue in some variable which will make L0 to be positive. Okay, we define it there and then we come back to the value of L0 that we want. We directly have to deal with the L0 less than or equal to 0 states for which this is divergent. But as we discussed earlier, that using string field theory, you can try to make sense of divergent integrals of this type. And in fact, at present, string field theory seems to be the only way to deal with these divergences. And we will see this with some examples. Okay, so let me now try to be more focused. That suppose we want to calculate the d-instanton contribution of the closed string endpoint function to first subleading order. So let's look at the ratio of the leading term to the ratio of the first subleading term to the leading term. So from the diagrams that we drew, okay, we can easily convince ourselves that at the first subleading order in G string, we need to compute these three ratios. This two-point function to the product of this one-point function. The reason is the following. If you remember this diagram replaces the product of two disk one-point functions by a disk two-point function. Okay, so if you try to calculate the ratio of this to the leading contribution, you will get the ratio of the disk two-point function to the product of two disk one-point functions. Similarly, this one it replaces a disk one-point function by an annulus one-point function. So you will get a ratio of the annulus one-point function to a disk one-point function. And this, of course, just multiplies the whole product leading term. So we need ratios like this or like this or this contribution over here, and to this you have to also add the torus with one boundary. Okay, that where you connect the two holes by hand. Okay, I just haven't drawn this explicitly, but that also should be included as part of this. So I'll denote this by some function p f of the energy momentum of the two external states p1, p2. I can call this another function g of the energy momentum of the external closed string states, and this is of course just a constant. So the first subleading correction to the endpoint function normalized by the leading term is given by a term like this, okay, where I and j run from 1 to n. Okay. This contribution comes from ratios like this, and the sum basically reflects the fact that we can take any pair in these lines, right? If there are n external states, there are n choose two choices for what we take these two closed strings, and that's what this sum represents. Similarly, this one can be any one of the n external states. That's what this sum represents, and this, of course, is a constant. So this is so far very general. Now let me describe what BRY found. Okay, this is the result that Victor described in his talk. Okay. So they computed this in the C equal to 1 string theory, okay, where the external closed string states are specified just by their energies, okay, which I'll denote by omega. So this function f, omega 1, omega 2, this is a two-point function, is given by some finite number, which is of course very complicated because this involves integrals over the finite integral over the moduli spaces. But then there is a divergent piece which is given here. Similarly, they also computed g as a function of the energy, and again we have a finite piece, and then you have a divergent integral of this kind. So you see that f diverges from the y equal to 0 end, and g diverges from the x equal to 0 or the v equal to 0 end. So at this stage, we will just leave it like this, but just parameterize these divergent parts. Okay, see here you see that there is a omega independent divergence, right? That I'll call AF, and then there is a omega dependent divergent term that I'll call BF. Similarly, for g of omega, there is a omega independent divergent part which is here, and then there is a omega dependent divergent part which I'll call BG. Okay, so here again I have written the parameterized form. So with this, we can now calculate the first subleading correction to the endpoint function, normalized by the leading term, and that's given here. Okay, this is exactly what we had earlier. Let me remind you. It's this formula over here, specialized to the C equal to 1 case. And now substitute these expressions over here. Finite pieces, of course, give finite result, okay, which we'll set aside. Okay, this, in fact, BRY evaluated numerically. If we see that this is, of course, as a constant, and there are n choose 2 such pairs, so AF is multiplied by a factor of n into n minus 1 by 2. AG will be multiplied by a factor of n because there are n such terms in the sum. The interesting case is of this one, BF and BG. Now here you will get BF sum over I less than j omega I omega j, but this can be rewritten as sum over I omega I square by 2 once we use the fact that at the end we will impose energy conservation. Right? We will use sum over omega I equal to 0, and using this relation we can easily verify that this sum is the same as this sum. So this shows that these constants BF and BG appear in the final formula in this combination. Okay, this is going to be important, that so BF and BG do not appear individually. Okay, it always appears in this combination in any endpoint function. And the k, of course, is just constant that doesn't get multiplied by any factor of n. Okay, so now I'm going to first give you the results of string field theory. What do we get at the end of this? So here again I have given the explicit expressions for AF, BF, AG and BG, right, the divergent parts. So what we will see is that once we use string field theory to analyze this, we get a finite unambiguous result, and that's given here. We get AF equal to minus half, AG equal to 0, BF equal to log lambda square, and BG equal to half log lambda square by 4. Lambda here is an arbitrary parameter. This enters the formulation of string field theory. In fact, string field theory, when you formulate string field theory, it's not unique. There is a whole class of string field theory, the infinite family of string field theories that we can construct, but they are all related by field definition. So the idea is that even though string field theory is not unique, the non-uniqueness is only up to field definition. So at the end, all physical results should be independent of what kind of string field theory you use. And here we see a reflection of that BF and BG, we see that does depend on lambda, which is this arbitrary parameter that appears in string field theory. Nevertheless, if you remember, the combination that enters the actual physical amplitudes is 2Bg minus Bf, and indeed we see that the lambda dependence cancels out in this combination. 2Bg minus Bf has the log lambda square cancelled out, and so you just get log 4, minus log 4. 2Bg minus Bf just as minus log 4. On the other hand, BRY determined these results by demanding that the finite part plus the divergent part is equal to the result in the conjecture dual matrix quantum mechanics. And they have to do it numerically because the matrix part, in the matrix quantum mechanics, the results are known in closed analytic form. But the finite part had to be evaluated numerically. It involves complicated integral. Okay, they have to evaluate it numerically. But then after evaluating this numerically, they compared the results on two sides, and then they found that the two sides match provided you choose the coefficients in this way. And we see that these string field theory results are indeed perfectly consistent with the numerical results that they found. K in principle should be determined, but it has not been determined so far. It requires calculating that disk with two holes, right, which has more moduli, so this has not been calculated. But in principle, one should be able to calculate this and get the result 0. Okay, so let me summarize the field theory results and then I'll try to indicate how we actually derive it. Okay. So the field theory results is that we have these divergent integrals AF, BF, AG and BG, and once you pass this to the machinery of string field theory, you get a perfectly finite result for all of these. So in the rest of the talk, I'll try to describe how this is achieved. Okay, at least I'll try to give the calculation of AF and BF, okay, and then I'll briefly indicate how these are calculated. Okay, so now I come to the string field theory analysis, and here we'll actually see how we go back and forth between the worldsheet and the string field theory description. I said that the Q parameters become the moduli of the worldsheet theory, and we'll see it explicitly during this analysis. Okay, so to proceed, first you have to understand, okay, the formula that BRY wrote. Okay. They had a y integral. If you remember, the expression for f involved a divergent integral, okay, that was an integral over this y parameter. Okay. So you have to understand what this y is in the worldsheet description. Okay. And this is what it is. In fact, Victor also drew this diagram. So this 2-point function, okay, can be mapped to upper half plane 2-point function, because this is the same as upper half plane. Upper half plane has 3 conformal killing vectors. Okay, there is an SL2R symmetry. Using this, we can fix 3 of the parameters. So we fix one of the closed string vertex operators at I that takes care of the 2 of the parameters, and the other closed string vertex operator we can put on the imaginary axis. Okay, so this fixes 3 parameters, and then you are left with the actual location of the closed string vertex operator on the imaginary axis, which are denoted by IY. Okay. And this is the y integral that we had in the BRY form. So the idea is that we will try to represent the disk 2-point function, okay, as a sum of Feynman diagrams in string field theory, and then try to identify the origin of the divergence as y goes to 0. And the relevant Feynman diagrams that we have to compute are these. This is a closed, so the notation is that thick lines will denote closed strings and the thin line will be open strings. So we have a Feynman diagram where we have an internal open string. Okay, this is in fact will be the origin of the divergence. because this is the open string propagator, and this is a contact interaction, two closed strings. So to compute the first Feynman diagram, we see that the open string here is internal. So we need the interaction vertex of an off-shell open string and an on-shell closed string. The closed string, external closed string is on-shell, so there is no issue with this. Because the open string is off-shell, it's not conformally invariant. So we need to choose a particular coordinate system at the open string puncture. Because this off-shell interaction vertex between the closed string and open string will depend on what coordinate system we use to describe, to insert the open string. I think in the next slide it will become a little clearer. So here is the description of the closed open interaction vertex. So closed open interaction vertex, okay, again we look at the upper half plane, and here we see that we can fix all the positions because closed string has two moduli, open string has one modulus. So altogether 3 variables, we can use SL2 to fix all 3 variables. So you put the closed string at I, open string at the origin. But we need more information because you have to say which coordinate system we use to insert the open string at the origin, because open string vertex operator is off-shell. And I'll make a simple choice. Okay? The final answer should be independent of what choice you make. You can choose anything that you like here as long as this function W is analytic near the origin. Okay, that's all it is. Otherwise, you can use any function of Z to insert the open string, but I'll take W equal to lambda Z. Okay, just for making things simple. Okay, and we'll take that lambda as an arbitrary constant here. So this means that if the open string vertex operator V has dimension H, then we insert this combination. Instead of just saying that you will calculate the vertex operator of closed string here and the vertex operator of open string here for this 2-point function, we multiply this vertex operator by lambda to the minus H, because when you go from W to Z coordinate, you scale by lambda. Okay, and this is the form of the vertex operator in the Z coordinate. And as I have already said, different choices of lambda will lead to different string field theories, but they should be all related by field difference. So final physical results should depend on this lambda. Okay, so let's go back to this diagram again. So there are 2 ways of computing this diagram. One is that we take this open closed vertex that we introduced and we just explicitly sum over all internal open string states. So you compute the closed open vertex, use 1 over L0 as the propagator, and in the vertex you also put this lambda to the minus H factor, and then you sum over all the open strings in the intermediate chain. That will be a direct but a more complicated way of doing this. However, because of the conformal word identities, we can give a simple interpretation of this, the same diagram, okay, this infinite sum over all the open string states, if we use the Swinger parameter representation of this propagator. If you use the Swinger parameter representation of this propagator, then it turns out that there is a simple rule for translating diagram A to the worldsheet description, and that is to take 2 copies of the upper half plane. Okay, we call this the Z plane and the Z prime plane. Z plane associated with this vertex, because this vertex has the one upper half plane, right, Z plane, and similarly the other one will have another Z prime plane, and then we just show them together by this identity W prime equal to minus Q. Q is the same Swinger parameter that appeared in the description of the property. And using the fact that W is equal to lambda Z, we can translate this to lambda square Z prime equal to minus Q. So we see that originally the closed string punctures were located at Z equal to I and Z prime equal to I in these 2 vertices. But now the Z and Z prime plane have fused together, become one by this relation. So we can translate the location Z prime equal to I in the Z coordinate system, and that's given by IQ over lambda square. Okay, if you say Z prime equal to I here, you get Z equal to IQ over lambda square. And now you compare this with this diagram over here, right? The one vertex operator at I, one vertex operator at IY, to conclude that Y is related to Q for this diagram by as Y equal to Q over lambda square. And this is the way we convert the worldsheet parameter, the string field Schwinger parameter Q into the worldsheet parameter Y. So Y is Q over lambda square. And so because the range of Q was from 0 to 1, in the Y variable, this becomes from 0 to lambda to the minus 2, 0 to onward lambda square. So now the idea is that we divide the Y integration region into two parts. One is from 0 to 1 over lambda square. This corresponds to the range 0 to Q less than 0 less than 1. And then the rest of the range, 1 over lambda square to 1. And then we say that the first range is coming from the diagram A. And then whatever is left is coming from diagram. Okay, that's the way you identify the worldsheet contribution to the string field theory. Okay, so we have this change of variable. So let's take the first range, okay, and the same integral that we had, the divergent integral that we had earlier, and rewrite this in terms of Q. Okay, so this integral in terms of Q just becomes this, and now we compare this with this identity, integral 0 to 1 dq q to the L0 minus 1. So you see the first term q to the minus 2 corresponds to an L0 equal to minus 1 state. So that's easy. L0 equal to minus 1 state will give minus 1, right? So this integral dq q to the minus 2 is just replaced by minus 1. Second one is the troublesome one, that corresponds to L0 equal to 0 state. But we can ask, what is this L0 equal to 0 state that is propagating in the propagator? And that in fact one can show is just the open string 0 mode that describes the d instant on location tau in time, Euclidean time. This is what Victor called x naught. And if you recall, we are required to integrate over x naught at the end. So this path integral over tau needs to be performed at the end, and in fact this is what is needed to eventually reproduce the energy conserving delta function from this identity. So because this path integral is performed at the end, okay, path integral here is just ordinary integral, right? Because they are 0 dimensional fields. So because this integral has to be performed at the end, we should not also include its contribution in the propagator. That will be doing it twice. So the 0 mode integral, as in all instantaneous expansion, has to be done at the very end. So you should remove the 0 mode contribution from the propagator. That basically means that you should just drop this integral dq q inverse. You should just drop. Okay, it is to be done at the end. Okay, so now we are in business. So this integral, this is a divergent part of the integral, we convert it to q integral. Then the first term we replace by minus 1, right? Because integral dq q to the minus 2 is 1 over L0 for L0 equal to minus 1. Second term we just drop, so it just gives you minus half lambda to the minus 2. The second integral, this is the contribution to diagram B. This is a finite integral. You can just do it. It's given here. And so you just add them. Add this with this. And you get minus half plus omega 1 omega 2 log lambda square. And this gives you AF equal to minus half and BF equal to log lambda square. So this gives us the result that I had quoted already. Similar analysis can be done for the divergent part of the annulus one-part function. Okay, here in fact it's more complicated, so I'll not describe the analysis in detail, but the principle is the same. So the first thing we have to understand is that we have this divergent integral like this. We have to understand what these parameters are in terms of the worldsheet. And here is the description. So you can think of the annulus as a cylinder. We can normalize, so the height is always pi because you can always scale the cylinder. Then the circumference is a variable that you have to integrate over, and this v is basically determining the circumference by this relation over here. And the height of the closed string vertex of pattern from the bottom is what we call 2 pi x, right? That's the interpretation of this variable x. And so the idea is that we treat these divergences by rewriting this annulus one-point function as a sum of Feynman diagrams, and the relevant Feynman diagrams are given here. Again, the thick line is the closed string propagator, the thin line is the open string propagator. So all the internal propagators in fact are open string propagators. And the idea is again that for each of these Feynman diagrams, we have to convert these variables q1, q2 into x and v. And then we rewrite these divergent integrals in terms of q1, q2 integrals and then interpret them. Right? If it's dq q to the minus 2, you replace by minus 1. If it's dq q inverse, you just drop it because we are not supposed to integrate over 0 modes in the internals. But there are some additional complications that you have to deal with. The first complication arises from the fact that the string field theory gauge fixing that leads to worldsheet rules actually breaks down in the L0 equal to 0 sector. And the net upshot of this is that we have to allow an out of Siegel gauge mode, which is C0 on the vacuum, to propagate in the open string propagator. Which basically means that in each of these diagrams, besides dropping the 0 mode integral and reinterpreting dq q to the minus 2 as 1 over minus 1, we also have to explicitly insert the propagator for C0 on the vacuum. Okay, C0 on the vacuum. So for each of these propagators, you have to insert C0 on the vacuum and sum over all those quantities. Okay, so this is an additional complication that you have to deal with. And the second complication that you have to deal with is the relation between the string field theory 0 modes and the canonically normalized 0 modes of the D instanton that can get corrections at beyond the leading order. And this means that we have to rewrite the string field theory path integral over the string field theory 0 modes in terms of the canonically normalized 0 modes, and in that process you pick up a Jacobian. And it can give additional contribution to the amplitude. But all this can be done systematically, and after doing all that you get these final results that I had quoted earlier. So this calculation is straightforward, but it's much more involved than what I had described earlier. Okay, so now I come to the final slide, okay, and which in fact is more or less identical to I think Victor's final slide, okay, and which is what else can be done or what else has been done based on these kinds of string field theory analysis. And indeed, this kind of analysis by now has been used to compute D instanton amplitudes in a wide class of compactifications of string theory. And here is a list. I think I have included most of the things, but I may have missed also some things, I don't know. C equal to 1 bosonic string theory is what I described. Okay. C less than 1 bosonic string theory. These are critical string theory, type 2B in 10 dimensions. Compactifications of type 2 and type 2B on Calabi-Yau threefold. Type 2 and type 2B on Calabi-Yau orientifolds. These are n equal to 1 compactifications. Then the C hat equal to 1 type 0B, sine Liouville deformation of C equal to 1 bosonic string, and these two non-critical strings. And finally, I should just say that when the result is known from a dual description, like the matrix theory, or in the case of type 2A and type 2B, the S duality, this procedure produces the correct result in all cases that have been studied. Okay, so this is a good test that this method is working, but this method has also been applied to cases where there is no other method to compute things. For example, we computed the superpotential for compactification of type 2 and type 2 on Calabi-Yau orientifolds, okay? And here there is no other method. Okay, so string field theory is the only way you can get sensible result for the superpotentials for these theories. Okay, thank you.
The parameters into the parameters.
Yes.
Popper similar, at least in spirit construction, where the finger parameters of the QFT and preludes get organized into the ATS radius. So is there a connection, or is this just a random?
Yeah, the point is string field theory is more versatile because here you don't have to specify a particular parameterization. You can, for example, this choice of lambda, right? That's only one particular class, but as I said, the relation between W and Z could be taken to any function, any function that is analytic around the origin. So this parameters that you're talking about is a very specific parameterization of this off-shell variance, but that is not needed for this analysis, right? This analysis is valid for general choice of off-shell variance. In heterotic string? Well, heterotic string of course doesn't have d instantons, right? But there are various applications of string field theory even for heterotic string. Right? For example, when you want to calculate the mass renormalized, suppose you have a heavy state whose mass is renormalized, then you cannot use the standard Ornstein methods to calculate the mass renormalized. Because what happens if you think of how you calculate mass renormalization in quantum field theory, you have to look at the 2-point function for generic k and then look for where the pole is, right? So to begin with, you have to get the off-shell 2-point function, right? And then look for the pole in the momentum plane. So you need off-shell formalism, and for that you need string field theory. So that's one application of string field theory in heterotic string, but this is not in the context of instantons because you don't have the instantons in the heterotic string. Yeah, I mean this Deligne-Mumford compactification. Yeah.
Yes.
Yeah, it will be nice if it can be interpreted that way, but I don't really know how to do it, right? And one reason is that this, I mean, you see from this picture that individual diagrams are ambiguous, right? We saw here that there is a lambda dependency. If you look at these expressions, BF and BG, right? This is this 2-point function, this is annulus 1-point function, right? Each of them have ambiguities, right? And it's only when you combine them, right, in the way they appear in the S matrix that the ambiguities go away. So it's not completely clear how the Deligne-Mumford kind of compactification will relate the ambiguities that arise in these two different diagrams. Right? Maybe there is a way to do it, but at least I don't see it immediately how to do it.
String field theory allows some non-geometrical, like not complex space, and some
Non-geometrical background?
yes.
Yeah, it could allow non-geometrical background, which doesn't have a simple interpretation. Right? For example, the open string tachyon vacuum is probably a kind of that, one of that kind, right? Which doesn't have a clear geometric interpretation. Now, in the closed string sector, yeah, in principle, it could give rise to non-geometric background, but so far, string field theory is being used only to only perturbative. I think what you are asking is whether string field theory can have solutions which are order 1, which are not small, and which doesn't have an interpretation in terms of some background metric. It is certainly possible, but I mean, we don't know of any solutions of that kind in the closed string field theory. Yeah, I mean, so far, no. I think one has to proceed systematically. I mean, we know in some cases there should be 5-brane corrections, for example, right? The NS 5-branes, and that will be the next thing one should try to study, right? How to systematically compute corrections due to NS 5-branes, and then one can try to go into more general kind of background. So far, I don't think. I think for NS 5-brane, if I understand Sergey and his collaborators, they have estimated what the non-perturbative corrections are, but that's using S duality. I don't know, you can probably clarify. If I understand one instanton corrections, you understand, right? Yeah. So it will be, I mean, so those will be the first thing to study. Since you have an answer, right? We should first try to reproduce them systematically from string theory side, and then maybe we can try to generalize to other cases.
So you find those cases show that the example.
I wouldn't say that we have shown this, but if we expand the matrix model answer in the instant-on expansion, the results agree. Now, you are asking whether the matrix model answer expanded in the instant-on expansion gives the full non-perturbative result. Okay. I don't know how to answer that question. Maybe Victor has. The question is, do we know that if we take the instant-on expansion of the matrix model result, that's complete? But those are probably not included in the S matrix that we constructed, right? The matrix quantum mechanics doesn't have those. Yeah. So if you just expand the matrix quantum mechanics, it looks like that the instantons are everything, right? Yeah. Yeah. So at least there is no immediate sign that it contains anything other than the instantons when we expand it out. Page 13, okay.
About the function involved sweep, P1, P2 sweep.
Yeah, so those will be suppressed by one more part of G string, because if you have P1, P2, P3, right, that means say we have disk with 3-point function, 3 insertions. So you are giving up 3 disks, one, and converting it to 1 disk. See, every time you lose a disk, you lose a part of G string. So a 3-point function will come if you take product of 3 disks and replace it by a disk with 3 insertions. Right, so you are losing effectively 2 disks. So that's in order GS square correction. So in order to order GS, you don't get anything else, right? Because you only get these pairs over here. Is that point clear?
So again.
Thank you.